Baghdad of the 9th century must have been a marvelous and exciting place. In the last lecture, we talked about the translation movement that took place largely in Baghdad, although in other centers as well, from about 750 to about the year 1000, where huge numbers of Greek and Persian and Indian texts were translated into Arabic. Now, in this lecture, I want to go a little bit further to talk about the contributions of Arabic authors themselves in the sciences. And we'll start with astronomy. Well, astronomy, as you know, was one of the high points of classical Greek science. Astronomical calculations, astronomical systems, cosmological speculations were all developed to a high degree in the ancient Greek world. Astronomy was also taken up avidly in the Islamic world, and Arabic astronomers made significant contributions. For example, one of the first books that was translated out of Greek was Ptolemy's Almagest. In fact, nowadays, we still use the Arabic title, not the Greek title, for the Almagest. That's how it was translated into Arabic. It's actually a compilation of a Greek and an Arabic word. You might want to keep an eye out in daily parlance for words that start with the letters AL. It's the Arabic definite article the, and so a lot of words in the English language that start with AL are actually of Arabic origin. Now, the importance of Ptolemy's Almagest to the Muslims, like to the Greeks, was only partially astronomical. It was also of astrological importance. I already mentioned how the date for the founding of the setting of the foundation stone of Baghdad was chosen astrologically. Well, in fact, the Almagest and Ptolemy's Tetrabiblos, that other work that has to be read alongside the Almagest, which is the key of what the astronomical positions actually mean astrologically, was also translated into Arabic. Arabic astronomers produced new star charts, improved methods for calculation of astronomical events, and calendrical reckoning. Now, if you go outside on a dark night, you look up in the sky and you pick out the brightest stars. To this day, about half of those bright stars have Arabic names, which is a constant reminder of the importance of Arabic astronomy and how influential it was in the development of European astronomy. Stars like Betelgeuse, Deneb, Vega, Aldebaran, Mizar, Algol, Altair, Rigel. These are all Arabic names. These were all names given to the stars during the Islamic Middle Ages, which were then transferred to the Latin Middle Ages. Many astronomical terms, in fact, are also of Arabic origin. The highest point in the heavens is the zenith, an Arabic word. The lowest point, the nadir, also an Arabic word, as is the azimuth, which is the angle between a celestial object and due north. Now, besides observing and calculating the heavens, the Arabic writers also designed and improved astronomical instruments. And the one astronomical instrument that is most important for the Islamic Middle Ages, as it would be for the Latin Middle Ages, is the astrolabe. Now, this is a cardboard copy of an astrolabe. The original ones would have been made out of brass, so they would have been much heavier than this. But the astrolabe is a remarkable device. It's used for observation, and it can also be used for calculation. So, for example, if I hold it up to the sky and use this called the alidad, again an Arabic word, I can sight through it to determine the altitude of the sun or a star. Why would I want to know the altitude of the sun? Well, if I know the altitude of the sun and the date, I can turn it over onto the back and use, I'll describe what this is in a moment, but use these sliding scales and this rule to calculate the local time from the position of the sun. I can also use it as a calculating device. I can figure out at what time on any day of the year any bright star or the sun will rise and set. I can also figure out astrological data, figuring out about the various houses and the position of the sun in them. Let me explain exactly how this works. The astrolabe is itself not an Arabic invention. It's a Hellenistic, Greek invention. What it is, it's a flattened map of the heavens. If we look here, and we can see on this surface these lines, which represent the lines of latitude and longitude in the heavens, as if we took the dome of the heavens and squashed them flat. Moving over that is this object called the rete, which is actually a Latin word, a net, which has pointers which allow you to line up where stars would be on that map of the heavens. There's then also this rule, which can be used to read off from the points of intersection of the stars with the band of hours on the outside to tell you something about their rising and setting times. So, a very useful device. You can calculate almost anything you want to know about astronomical times of rising and setting, local times, latitudes, using the astrolabe. One Arabic writer by the name of Ali ibn Isa was known by the epithet al-Asturlabi, the astrolabist, because he wrote so much about the astrolabe. The astrolabe not only was improved in the Islamic world, it was transferred eventually, as we'll see, to the Latin West, and astrolabes were in use as astronomical devices down until the 17th century in Europe. Even they existed alongside the telescope for a while. Other instruments that were invented were the Qibla finder. Remember, the Qibla is that direction towards Mecca. Well, if you're stuck out somewhere in Morocco or Spain or India, how do you know the direction to Mecca? Well, Arabic astronomer mathematicians devised little devices that you could carry around with you, which, using the position of the sun or the stars, could tell you the correct direction, allow you to calculate the correct direction in which to pray. Now, let me mention a few Arabic astronomer mathematicians in order to give you an idea of the scope of mathematics and astronomy in the Muslim world. Let me start with one that I've already mentioned. This is Thabit ibn Qurra, who was born in 836, died in 901. He was the Sabian. He translated and commented on a lot of works, but also did his own observations. Let me just mention some of his own writings. He wrote a commentary on Aristotle's physics, as well as a commentary on Ptolemy's Almagest and the Tetrabiblos. He preserved writings of Archimedes. Indeed, Archimedes came to the Latin West first through Thabit ibn Qurra's translation. Moreover, there are some treatises of Archimedes which are lost in the original Greek. And the only reason we have them is because of the Arabic translations, many of which were made by Thabit ibn Qurra. He wrote on parabolas and other conics, like Apollonius, the Greek mathematician, had done. He wrote tracts on all kinds of things. He wrote nearly 70 books. He wrote a work on why the sea is salty and proposed reasons for its saltiness. He wrote on music. He wrote on medicine. He wrote an exhaustive treatise on the construction and calculation and use of the sundial, which is widely used. He also did some observations which told him that the length of the Julian year, that is, remember the Julian calendar, 365¼ days long, figured out by Sosigenes the Egyptian for Julius Caesar. The length of the Julian year, Thabit ibn Qurra figured out, was off by 1 day in 130 years, which is an extremely accurate prediction. In fact, or not prediction, I should say, measurement. It's an extremely accurate measurement. Sosigenes' year was off by 11 minutes. And those 11 minutes are basically, out of the whole year, that's what Thabit ibn Qurra discovered. In fact, when the Julian calendar was amended in the 16th century by Pope Gregory XIII, this was one of the calculations that was used. Thabit ibn Qurra's work was pretty close, 1 day in 130 years. Now we use 1 day in 125 years is the correction of the Julian to the Gregorian calendar. That's pretty good. I should mention again that as a Sabian, his family was interested naturally in astronomical issues because the Sabians were basically star worshippers. And we find, in fact, that in the first generation of Muslim, or I shouldn't say Muslim, of Arabic-speaking, Arabic-writing astronomers, a great many of them are Sabians or come from Sabian families. So this is an interesting example of how a religious background can influence one's choices of what to study in the history of science, or what to study in scientific endeavors. Let me move to another astronomer, Al-Battani. Al-Battani was a little bit younger than Thabit ibn Qurra. He was born around 858, died in 929. He was certainly the best known of the Arabic astronomers in Europe later on when his work made its way to the Latin world. He was known as Albategnius in the Latin West. In fact, Al-Battani, under the name of Albategnius, was still being cited in the 16th and the 17th century as an authority. Copernicus, the great Polish astronomer, read Al-Battani and cited him. So clearly that's for 800 years his works were still being read. He made more accurate determinations of the lengths of the seasons. Remember, one of the problems with the old Eudoxian system was that the seasons are of different lengths. You can't divide the year into 4 equal points by the equinoxes and the solstices. In fact, the periods of the seasons are different, and Al-Battani clarified the lengths of the seasons. What he did also was to introduce trigonometry for the first time to the calculation of astronomical data. Prior to this time, the Greeks had always used geometry, and solely geometry. Ptolemy had the idea of the chord, which is akin to our idea of the sine, but that was only, he didn't really use trigonometry as we're familiar with it in calculation. That's actually an innovation brought into astronomy by Al-Battani. He made a lot of observations as well. He observed the differences, the changes in the apparent size of the solar and lunar disks. This allowed him to predict the possibility of such a thing as an annular eclipse. Now, he never saw one, and there was no record, as far as I know at least, of any of an annular eclipse ever having been seen. What is an annular eclipse? That's when the moon's disk moon is particularly far away during the eclipse, and so the sun's disk is larger than the moon's disk, and when the moon moves in front of it, you can still see a ring, an annulus in Latin, a ring of the sun around the moon, an annular eclipse. So he predicted that these were in fact possible, and he was right. He did observe a solar eclipse, not an annular one, at Antioch on the 23rd of January in 901. He observed a lunar eclipse at the same place a few months later. He also discovered the movement of the line of apsides. Now, what on earth is that? The line of apsides is the line that marks the place where the sun and the earth are furthest apart. If you want to think about it in the modern terms, it's the major axis of the elliptical orbit that the earth has around the sun. For them, it's the line that shows where the sun is furthest away from the earth. So think about it this way. We're standing here on an immobile earth in the middle of the universe. We watch the sun until it's at its furthest distance away from us, so its disk is smallest. It's receded into the background as far as possible. That line is the line of apsides, the line between the earth and the sun, and it must point at some constellation in the zodiac. Well, what Al-Battani recognized was that it wasn't always pointing at the same sign, because he had Hipparchus's calculations, Hipparchus's observations, which by his time were over 1,000 years old, and in that 1,000 years, that line had moved into a different constellation. And so Al-Battani was able to calculate that that line moved about 1 degree of the 360 degrees in the zodiac every 66 years. Clearly, he was a careful observer. He again commented on the Tetrabiblos. He made instruments. and wrote a large number of texts. Let me move on to my third character, Ibn al-Haytham. Now, he's known to the Latins as Alhazen, and that's the name under which he is most commonly called. He's yet a generation further on. He is 10th and 11th century, born about 965, died in 1039. Well, he did quite a lot of things. He criticized, for one thing, the disjunction between Ptolemaic cosmology and physical principles. Remember that there are some problems with Ptolemy. He moves the Earth out of the center of the universe and makes the orbits of the planets eccentric. He has epicycles where the planets are on this epicycle moving around a point on the deferent, and there's nothing at that point. And so there are problems when you try and relate the dynamics of physics of the time to the Ptolemaic system. They clash in certain places, and Alhazen was very sensitive to this and tried to work it out. He never did succeed in working it out, but he did start a discussion about this problem that continued in the Islamic world for several centuries. I should mention a little bit about his life, because his life is quite interesting. What does an Islamic scientist, if we want to use that slightly anachronistic word, do? Well, we know a lot about Alhazen's biography. Some things are contradictory, but nonetheless, I'll give you sort of a compendium of the best attributed material. It's said that he was invited to Egypt by the leader Al-Hakim, who reigned in Egypt from 996 until 1021. Alhazen was invited there because he claimed he would be able to stop the flooding of the Nile, to control the waters of the Nile. So Al-Hakim brought him in. Alhazen took a trip up the Nile. And the further he went, the more disappointed and disillusioned he got, because he realized that the lay of the land in the upper Nile was not what he thought it was. And so the flooding wasn't caused exactly by the principles he imagined. And moreover, he tells us that as he went up the Nile, he saw these immense monuments that had been built by the ancient Egyptians. And the more of them he saw, the more puny he felt. And he realized that if the ancient Egyptians couldn't stop the flooding of the Nile, he couldn't do it either. Well, he returned to Cairo and was afraid that he would be punished for his failure. Al-Hakim was known to be erratic and a man of bad temper. And so what Alhazen did, according to the story, is that he pretended to have gone insane. And he feigned madness until Al-Hakim died. And then he was back to his normal senses suddenly. He supported himself for the rest of his life in an interesting way. Once a year, he would make a copy of the Almagest, of Euclid's Elements, and of the related texts of Euclid, and sell them. And that brought him enough money to live for a year. He was connected to the mosque of Al-Azhar, where Al-Azhar University is now, for the rest of his life. So after the death of Al-Hakim, so that would be for the next 18 years. Well, considerable advancements in mathematics also occurred in the Islamic world. One of the most notable achievements was the introduction of place notation, the numerals that we still call today Arabic numerals. Now, this system was actually originally Indian, and the Arabs referred to it as Hindu reckoning. It was transmitted to Europe through a handbook written by one Al-Khwarizmi, who flourished about 825. He was connected with the Baitul Hikmah, the House of Wisdom in Baghdad. He was patronized by the Caliph Al-Ma'mun. A key feature of this system was the use of the zifr. Now, what is the zifr? Well, it turns out we get two English words, not just one, from the Arabic zifr. The first one is cipher, which is the figure of the numerals, but the other and more important one is zero. Right? Never before was nothing so important. Zero, as a placeholder, was something that the Babylonians, for example, in the first millennium BC, even though they had a place notation, they didn't have a place holder. So the zero saves us all kinds of confusion about knowing what places we're in. Now, Al-Khwarizmi did other things as well. He wrote a book which is entitled The Book on Reckoning by Completion and Balancing, which in Arabic is Al-Jabr wal-Muqabala. Now, if you listen to the first word carefully, Al-Jabr, which is the origin of algebra. Al-Khwarizmi wrote the earliest known treatise on algebra, the way of solving for unknowns by completion and balancing, that is, by moving terms from one side of an equation to another and solving for an unknown. He also wrote treatises on the astrolabe and on geography. So in addition to place notation, the zero, and algebra, Arabic mathematicians also essentially invented trigonometry. The Greeks had only one function, the sine function, but the other functions were added by Arabic mathematicians, the cosine, the tangent, the inverses. These were all Arabic contributions. Well, now having gone through astronomy and mathematics, let me get to my third topic, which is optics. Optics is another area in which the Arabic world made particularly important contributions. We have to back up a little bit, though, to talk about theories of vision in the ancient classical world so that we know what the problems were the Arabs were trying to solve. The basic problem, the fundamental problem of optics was that of how do we see? How does the image of an external object, whatever it may be, a dog, a cloud, a tree, a person, how does the image of that external object get transferred to our eye? Difficult question. There are three theories to explain this in classical Greek thought, in Hellenistic thought as well. So let's start with Euclid's version. Euclid studied vision, and like most of the Greeks, like Plato, for example, he believed that there was a visual ray that emanated from the eye. This is what is called an extromissive version of vision. That is, like a man with his eyes closed that reaches out his arm to touch to see what's around him, so the visual ray emanates from the eye until it contacts an external object, and then it tells us that it's there. How exactly it tells us is never worked out. Nonetheless, this was a standard idea. What was Euclid's particular contribution was to say that it emanated in the shape of a cone, which meant that it was able to be looked at using mathematical methods. We could calculate things like perspective, that things further away appear smaller based upon the opening up, the expansion of that angle of the cone as the visual ray leaves our eye. So Euclid's particular contribution was not the extromissive version, which was common, but rather the ability to calculate things geometrically, to use a geometrical version of vision. Very Greek idea. The second theory is a little stranger. It's the idea that the atomists had. They believed that every object was constantly peeling off its external surface, and that these very thin, what they called idola or simulacra in Latin, idola in Greek, would fly off of every object and enter our eyes. Now again, there are some problems with that, which were seen fairly quickly. If we go outside and look at a mountain, we say that some simulacrum is peeling off of the mountain and flying towards us. It's mountain-sized when it leaves the mountain, but somehow it's got to get inside our eye. That's a bit of a problem. Lucretius, the popularizer of Epicurus, says that the simulacra come off the way a snake sheds its skin, for example. Well, you know, if a snake keeps shedding its skin too much, too often, all the time, there's no snake left after a while. So that's another problem with the atomist view of vision. Nonetheless, there's a significant difference here. This is an intromissive version of vision. Something's coming into the eye, not going out of it. Aristotle promoted the third version, also intromissive. He says that objects change the quality of the intervening medium, generally the air, unless we're swimming underwater, but change the intervening medium, and so change the qualities in our eye to match the qualities of the object that's being seen. Well, the Islamic world inherited all three of these theories. The visual ray theory of Euclid, which is also upheld by Ptolemy, was agreed to by Al-Kindi, a 9th century philosopher in Baghdad. He wrote works on the visual ray and the reflection, the rays from other bodies, and we'll come back and talk about Al-Kindi because he turns out to be particularly important when his ideas get into medieval Europe. For now, though, let's look back at Alhazen. Alhazen produced a new view of vision, which combined the old intromissive and extromissive versions. In fact, he set the foundations for the way vision and optics would be handled scientifically, really down to the present day. And there's some problems with Alhazen's system, but nonetheless, it was very a useful one. What he did was this. His view, first of all, was intromissive. It was about light coming into the eye. The thing that he did that was important is that rather than having an Aristotelian qualitative treatment of vision, that qualities are changed, and rather than having an atomistic view with all the problems of the simulacra of a mountain shrinking to come into our eye, he instead used Euclid's cone, except turned it upside down. Instead of a visual ray emanating as a cone from our eye, the light comes into our eye as a cone. What does that mean he developed? He developed a ray theory, if you will, of light, or a conceptualization of light in terms of rays. Now, because any of us who have learned optics in the modern world say, well, rays, isn't that obvious? Well, we're familiar with it, so it's obvious. It's not necessarily obvious. It wasn't obvious for the first person who came up with it, Alhazen. This meant that he avoided the objections of the earlier theories. For example, he says, how is it possible if we go out at night and I suddenly raise my head to the heavens, does my visual ray immediately fill the entire universe so that I can see the stars? That doesn't make sense. So he got away from that problem as well, but keeping all the time the ability to deal with rays mathematically. There was one other problem he had to worry about. If you look around you, we see a lot of objects. And rays are coming off of every object in every conceivable direction, radially. How does our eye sort that out? Well, he proposed a hypothesis about this. Turns out not to be entirely satisfactory, but nonetheless it helped him do his calculations. He said that from every point on every object, there is exactly one ray, and only one ray, that impinges upon the eye, since the eye is curved, that impinges upon the eye at a perpendicular. Now think about that. There is one and only one ray from every point on an external object that hits the eye at a perpendicular. Well, Alhazen knew the laws of refraction. He knew that rays that come perpendicularly into a new medium are not refracted. Anything that comes at any angle that isn't 90 degrees is refracted. So his argument went like this. Any ray that's refracted is weakened and not sensed. Only the ray that comes in perpendicularly is actually sensed by the eye. Now think what that means for a moment. It means that every point is represented by exactly one ray, which impinges upon exactly one point in the eye. Therefore, we've transferred the image of all external objects point for point from the outside to the eye. It's a great achievement for Alhazen to have done this. Alhazen was seen as a master in vision and in optics. He wrote not only on vision, by the way, but also on burning mirrors, those parabolic mirrors that can be used to direct solar rays, concentrate them to set things alight. Surely he, like many of his contemporaries, knew the wonderful story of Archimedes supposedly setting the Roman fleet on fire in the harbor of Syracuse, and that was, of course, one incentive for studying burning mirrors. All right. Well, what we've done in this lecture is to look at three aspects of Arabic original contributions to the history of science, in astronomy, in mathematics, and in optics. In our next lecture, what we're going to look at is something that is in fact almost an Arabic original, that is alchemy. They did take some of it from the Hellenistic world, but it was developed to such a high degree in the Arabic world that we can almost think about it as an Arabic science.